Until 단위방은 이거 reduce it. Yes. Yeah, this one. Our great pleasure of Sari for the YIT seminar. And he is a very renowned researcher, having writing many influential papers, including the afterglow papers. And he got the PhD at the Hebrew University in 1998, and go to Caltech at the postdoc, and also he got a job at the Caltech, associate professor of astrophysics and planetary science, and go back to Hebrew University 2008. And now he's a chair of Center of Astrophysics and Planetary Science at Hebrew University. So today he will talk about dynamics in Galactic Center.
Thank you very much. Thank you very much. So I would like to talk about things that are happening in galactic centers. So both our own galactic center, but in galactic centers in general. And in this slide, I've collected a few of the phenomena that I want to describe. And the way I will organize this talk is we will go through these different phenomena. Some observations of stars in the galactic center, hypervelocity star, formation of hypervelocity stars, tidal disruption events, quasi-periodic eruptions, new phenomena becoming more and more interesting in recent years, and maybe sources of gravitational waves of low frequency that could come from galactic centers. So I'll describe a little bit of each of those. And then I will talk about the dynamical processes that lead to the sources of all these phenomena. So I will try to show what kind of orbits are needed for each of these phenomena, and how do stars scatter each other into such orbits, and therefore what is the rate of sources of this kind. So this is one of the field trips that we did from the Hebrew University. This is my group, my telescope, the Milky Way. See, the Galactic center is somewhere here.
Your own telescope.
This little one is my own telescope. It's 8-inch.
Okay.
But the real telescope is maybe this one. These are the two keck in Hawaii. Each one is a diameter of 10 meters. And the main group that is using these keck telescopes to do observations of the galactic center are the UCLA group. There's another strong team with the very large telescope, the VLT, in Chile, part of ISO. The main group again that is doing observation of this is MPE, the Max Planck Institute for Extraterrestrial Physics. Recently, they improved significantly the observational capabilities. This is maybe 5 years ago, by doing interferometry between the 4 VLTs in an instrument called Gravity. And by doing so, they get an effective telescope size of 150 meters. This is the distance between this and that. So the resolution is, to some extent, equivalent to a 150-meter telescope. So lambda over d, which is the theoretical resolution of an optical telescope, lambda is a micron for infrared light, is about 4 milliarcseconds. You can compare it to James Webb, which is not as good because it's a much smaller telescope, only 6.5 meters. Also, the overall collective area of 4 8-meter telescope is huge compared to JWST. So this is really a very powerful instrument. And for many of the purposes that following stars, orbits of stars in the galactic center, this is much better than what JWST can do. Okay. Yet there's still a room for improvement here because this system that collects the light from these telescopes takes the light in a very complicated path here until it combines here in this instrument. And a lot of the light, more than 90% of the light is lost. So even though there is huge collecting area, actually the number of photons would be less than what JWST would collect, but still resolution would be.
Probably the air condition affects the.
Yes, data problem too. So here you need adaptive optics, and there is. Here there's no need. But even with the best adaptive optics, the image is not as clear as an image from space. But still, resolution is better. So here is a movie showing observations. Just zoom in with an image from Earth towards the galactic center, so you see how crowded that field is. When you go deeper and deeper, you have to switch to infrared because the galactic center is opaque to dust. There's dust that is opaque to visible light, and only with the infrared, the opacity is not so bad, so you can still see through. This is now the innermost 1 arcsecond of the galaxy. This part.
This is VLT stuff?
This is VLT, yes. Before gravity, I think. Without this interferometry data. And you can see motion of the stars over 20 years of observations like this in this movie. You can clean it up, and you can actually fit orbits to the motion of these stars. And by studying these orbits, you can understand that there is a supermassive black hole in the center of the galaxy, measure the mass of the supermassive black hole from analyzing these motions, and actually also the distance from the galactic center. So as you know, this is the reason for the 2020 Nobel Prize in Physics. To those two guys, the UCLA group and the MPE group. And you can summarize maybe all of these observations by following this SO2 star. So this is one of the stars which has the smallest orbit around the supermassive black hole, and it's very bright. So the orbit around the supermassive black hole takes about 16 years. You can see the size of the orbit from the sky. That means that the semi-major axis is about 1000 AU. The closest approach distance is about 100 AU. So this means this is a very eccentric orbit, eccentricity of 0.9. This is only 10% of this. So the eccentricity is 0.9, very elongated orbit. And by using this number and this number, you can calculate the mass of the supermassive black hole, and it comes to be 4.3 times 10 to the 6 solar masses. So we know this number very accurately. In fact, by measuring radial velocities of this, it also enabled us to tell the distance to the supermassive black hole, not by redshift, but just by transforming the observed size on the sky to a physical size. Then it gives us the distance of 3.8 kiloparsec, 27,000 light years. So what was achieved with that? So certainty that there is a supermassive black hole in the galactic center and a measurement of its mass. They also managed to measure the gravitational redshift. So as the light is coming here, it has to climb the gravitational potential. So the light is redshifted. More recently, they have been able to measure the precession of this orbit. So this orbit, because of GR, precesses, and they see this precession. Now, once they install the gravity, they can see even more stars with orbits closer to the supermassive black hole. And if there would be enough of them, this is not sure yet, they might be able to measure the black hole spin. Because when you have an object around a black hole, the orbit precesses what we call the Schwarzschild precession. But if the black hole spins, there is an extra precession due to the fact that the space-time around the supermassive black hole is carried. If you want to think about it that way with the spin of the supermassive black hole. So this kind of precession has not been seen yet. But if it would be seen, it would be a direct measurement of a spin of this supermassive black hole, which is maybe one of the first real measurements of spins that we would have. But that requires closer stars that we are not sure if they exist or not. And some of the theory I will describe to you is able to predict whether stars like that exist or not. So even though they got the Nobel Prize, they did these fantastic observations, it's still not like this. This is what we would have liked to have. We don't have it. Do you recognize this image? I see it coming out of the screen like this. Anybody recognizes this image?
Yes, from the movie Interstellar.
Yeah, from the movie Interstellar. This is a black hole that in the movie they called Gargantua. It's a gigantic black hole, I think bigger than what we have in the galactic center, maybe billion solar masses and all these nice effects that are happening around it. We don't have images like that, but we do have images like that of M87 with, not as good as the previous one, M87 or the Milky Way, so just barely resolving the black holes in our own galactic center and in nearby galaxies. Okay, there's this intensive, it's called intensive lecture lecture on gravitational waves, and I'm sure you all know the gravitational waves LIGO detected, and Japan is now taking part in it in the KAGA project. And gravitational waves are now routinely detected, and another Nobel Prize given for this. Do we expect the gravitational wave also from the supermassive black hole in our own galactic center? Like all these many that were detected, why not from the supermassive black hole in our own galactic center? And the answer is that the frequency of gravitational waves that is emitted by the merger of two black holes is inversely proportional to the mass of the system. The bigger the mass of the black hole, the bigger the event horizon, the longer it takes to go around it, even if you go at the speed of light. and therefore the frequency is inversely proportional to the mass of the black hole. So in the galactic center, we have a black hole which is 1,000,000 times heavier than standard black holes, than stellar mass black holes, and therefore the frequency will be 1,000,000 times lower. So while LIGO detects normal black holes, stellar mass black holes, like those, in the 100 to 1,000 of hertz frequency range, if you want to detect black hole, anything merging a supermassive black hole in gravitational waves, you'd have to go to lower frequencies by a factor of 1,000,000. So instead of kilohertz, millihertz. The detector that will do that is LISA, the laser interferometry space antenna, which will be a collection of 3 satellites spaced by 2.5 million kilometers. Look at this number compared to 4 kilometers, which is the arm size of LIGO. So much longer, compatible with the longer wavelengths that you want to measure and compatible with the ability to make something like this in space, rather the difficulty to make something like this on Earth. And there will be 3 satellites which will trail the orbit of Earth, maybe 50 kilometers behind Earth. And the interferometry between those 3 will be able to measure the shaking of space-time, and they allow us to detect the gravitational waves. This is a little bit in the future. So again, at the end of the lecture, I will try to show what predictions we have for gravitational waves for LISA from the supermassive black hole in our own galaxy and in other galaxies. Yeah, maybe a summary of all kinds of gravitational waves detectors at different frequency. Currently, this is working very well. LIGO, LISA, factor of 1,000,000 in frequency, or almost 1,000,000. Pulsar timing array, which already gave some results, even lower frequencies. And also in the CMB, you can see at even lower frequencies some signal from gravitational waves. Questions up to here? Okay, so I'm going to talk about hypervelocity stars. This is a fascinating phenomena where stars observe that velocities of close to 1,000 kilometers per second, some more, some less, are observed to move readily out of the galaxy at these speeds, exceeding the escape velocity from the galaxy. So these are stars that are going out, never coming back to the galaxy. And the question is, how were they formed? What gave them this tremendous velocity? Now, there's something special about 1,000 kilometers per second. It's very big in some sense. In what sense? It's bigger than the escape velocity for main sequence stars. So if you take, for example, the sun, the escape velocity is 600 kilometers per second. And one way to produce stars that are moving fast is to put them in binary, and then to explode one of the members of the binary. And then the other star just moves with the linear velocity that the binary had. But the highest velocity you would have is when you have a contact binary. And the contact binary has a velocity which is a factor of square root of 2 below the escape velocity. So if you put 2 sun-like stars as close as you can, making them touch each other, you'll have velocities of 400 kilometers per second, much below 1,000 kilometers per second. So basically, just by dissolving a binary, you cannot have velocities which are bigger than 200 kilometers per second, or 400. But here we have 1,000. So how do we do that? There's a mechanism called the Hills mechanism, and it is depicted in here. You take a binary, so again a binary like we had before, but the binary itself cannot do it. You need something else. You need a supermassive black hole. You bring the binary on a very eccentric orbit till it gets so close to the supermassive black hole that tides from the supermassive black hole dissolve the binary. The binary came from very far away, therefore it has a 0 energy orbit in total. You break it into 2 pieces. One piece has negative energy, it is bound. The other piece has positive energy, it flies out. And it turns out that the velocity of this object that is flying out can be about 10 times bigger than the binary orbital velocity. So if before we said that the highest velocity you can have is around 200, 400 kilometers per second, now it's 10 times more than that. So you can have 2000 kilometers per second out of dissolving a binary in this method. These are the scalings. So the ejection velocity is the velocity of the binaries times m over m to the 1/6. M of the mass of the supermassive black hole, m the mass of the components of the binary. So this ratio is about 1,000,000. 1,000,000 times 1/6 is 10. This is why I said you can have 10 times larger velocity than the original velocity of the binary. So this black hole is a mechanism to increase the velocity by a factor of 10, allowing you to form hypervelocity stars. Okay. What do you need for that? To go back this slide, you need a binary. You need the binary to come on a very eccentric orbit, so it needs to come from far away and to come very close to the supermassive black hole. How close? What we call the tidal radius of the binary. And this is about the binary separation times the mass ratio to the 1/3. So let me derive that for you. So if you have, can you see this? The right more here, or is this? Can you see this? Yeah. Okay. So if you have two binaries with a separation of A and their mass is little m, and there is a supermassive black hole of mass m, you can ask yourself how close the binary has to come next to the supermassive black hole in order for the black hole to break the binary. So you want that the forces between the objects, Gm over A squared, would be smaller than the tidal forces from the black hole on the binary. So the force from the black hole on the binary, or the acceleration, is Gm over R tidal square. We want to find what this R tidal is. But this force does not break the binary. This just accelerates the whole binary together. We want to see the differential acceleration between the two. So we have to multiply this by A over RT. So you see that G cancels out. You have A cubed, RT cubed, and M over M. So you get that RT has to be smaller. The approach radius has to be smaller than the tidal radius. RT is when these are equal. RT is M over M to the 1/3 times A. Okay, so let's put some numbers in here. What is A? It's the separation of the binary. What separation of binaries we're talking about? Just a few times the radius of the stars, because we want high velocities. If the binary is too separated, the velocities are small. And even if you multiply this by a factor of 10, you still get a small velocity. So if you want high velocity, you should start with almost a contact binary and dissolve that. So A is just a few times the solar radius, if you're thinking of solar-like stars. M over M is 1,000,000, we already said. M over M to the 1/3 is 100. So we're talking about 100 solar radii, so about an AU. So the tidal radius is about an AU. To go back to the observations of our own galactic center, here, compare with the orbit of SO2. So SO2 has a semi-major axis of 1,000 AU, closest approach distance of 100 AU, but the tidal radius in order to destroy that star is just 1 AU. So no, it's not going to be destroyed. It's very far compared to what is needed to destroy the factor of 100. So it's safe out of the tidal radius. Even if SO2 was a binary, contact binary, that binary would have survived. Okay. Tidal disruption events, I'm sure you have heard about it and heard some talks about it. This is a very similar mechanism to this. But instead of destroying a binary, you destroy the star itself. But since we were talking here about binaries which are almost contact binary, with a separation of about a solar radius, this is like destroying the star. So the tidal radius here is also going to be about 1 AU if the supermassive black hole is like the one in our galaxy. And again, in the very same way that we had for the hypervelocity star formation, you get the star coming in, torn apart by tides from the supermassive black hole. Some of the debris get negative energy, some get positive energy. The ones that get negative energy, they're bound. They come back, eventually accrete to the supermassive black hole. And people now debate, when we see an event like that, we think we've seen many of them in distant galaxies, and we're not sure exactly what is the mechanism of the emission. Do we see the accretion of the material on the supermassive black hole? Do we see the collision between the material and itself, let's say somewhere here? Because we think that the actual accretion to the supermassive black hole takes a long time, depends on the viscosity, on magnetic fields in the disk, maybe longer natural processes we needed in here. The orbital time here for the material that just returns is about a month, and this is what we see in the tidal disruption events that we follow. The time scales here, as you see, is a few tens to 100 days, so a month to a few months. Observationally, the rate is a little bit lower than this, maybe once in 10,000 years per galaxy. But following many galaxies, you can see many of these. And now with the wide field of view surveys that are becoming more and more frequent, we'll see many TDEs. Okay, next topic, quasi-periodic X-ray eruption, or QPEs. This became fashionable in the last couple of years. What is this? It's emission of X-rays coming from centers of distant galaxies. So again, something related to center of galaxies, probably to the supermassive black hole in the center of galaxies. And these are eruptions that each one lasts maybe an hour, separated by several hours, like 10 hours, sometimes 20, 18, sometimes 7 hours, but this is the typical separation. Luminosity is about 10 to the 42 to 10 to the 43 ergs per second during the emission, maybe 10 times less than that between the emission, and the energy is about 100 electron volts, the relevant temperature associated with this emission. People argue what is the exact model for this. This is again an example of a few objects. We only know about 5 objects that are doing this, so it's not like many. And some of them have this weird behavior of strong pulse, weaker pulse, stronger, weaker, stronger. And also the separation is not always completely periodic, shorter, longer, by maybe 10%. So one of the first models was to say, okay, this is the center of some galaxy, maybe it's an AGN, maybe there's a star orbiting that supermassive black hole and goes through the disk of that AGN. And as it goes through the disk, it collides with the disk, and you see the emission from that collision. So this is a very attractive model because it has a periodicity, the orbital period of the star. Actually, it has 2 events per period, one here and one here. And if the orbit is eccentric, you would have this property that these 2 crossings are not the same, and the spacing between them is not the same. So if the orbit is eccentric, you can have this shorter or longer than the other part of the orbit. So many of the properties that we've seen, they can happen in this. The problem is that in more recent years, they detected several QPEs, events like that, from galaxies which do not seem to have AGNs active in them. So This made this model maybe a little bit less popular. Alternative models that came was that there is just a single object without a disk, a single star orbiting the supermassive black hole. And it comes in two flavors. The original one by King, that you have a very eccentric star, maybe a white dwarf. Model, I can explain why a white dwarf. And it penetrates the tidal radius, just like tidal disruption events that we've seen before. But it does that only very gently. So it doesn't get completely destroyed. So every orbit that it comes, it just barely goes through the tidal radius, just the outskirts of the white dwarf are getting destroyed. They accrete onto the supermassive black hole, and you see this episodic accretion every periapse passage. This is this model. We had a competitive model. We are saying that this is not a white dwarf, this is just a normal star. And the rest of the story is the same. Also has a slightly eccentric orbit, less eccentric than what in it. And it goes gently into the tidal radius, the outside of the star spills out, accretes into the supermassive black hole, and you get an emission. Here, the idea that white dwarf was needed came from the fact that an estimate that the mass transfer between the star and the supermassive black hole is stable. What we showed is that because of the very small distances that are involved in here, this mass transfer is unstable, and therefore even a normal star can produce the same thing. I think both these models probably have some problem with the observations. So I'm not sure neither of them is right. For example, explaining the long and short delays between events doesn't come naturally in this model. Strong and weak systematically does not come naturally in this model. So recently, my student, who is now my ex-student, who is now a postdoc in Princeton, Itai, together with Brian Metzger, they came up with a hybrid model between the disk model, the AGN disk, and the star that is going. They say the following. They say there is a star orbiting the supermassive black hole in galactic center. It does nothing. It just goes. Another star is coming, much closer to the supermassive black hole, and it gets destroyed by a tidal disruption event. That tidal disruption event creates a disk around the galaxy that didn't have any AGN before. This is a new disk just formed by a tidal disruption event that happened a year or several years ago. This disk is now there, and then you apply the original model. There is a star going through this disk, so they call the paper EMRI, extreme mass ratio in spiral. So this is just a star orbiting the supermassive black hole, plus tidal disruption events give you quasi-periodic eruption. And I think this is very promising, at least for some of the cases. Questions? And there is an evolving class of objects. There is now a paper calling a new object they found monthly QPs. So the period between one emission and another is not 10 hours like the previous objects I show you, but 1 month, 20 days between 25 days between one emission and the other. And there might be a continuation of all these systems, from TDs to QPs, to these monthly emitters. So these are objects that come close to the supermassive black hole, get destroyed, and they do that again and again. They don't get completely destroyed, just partially. Okay, so here, this is the end of the part where I described some of the phenomena that are happening in galactic centers. And now I want to talk about the dynamics that lead to all these phenomena. Now, why do we have to talk about it? Because all the processes that I described are destructive processes. They destroy the object that create them. But we're seeing these objects now. So if the old ones got destroyed, something has to produce these objects or new orbits that will have these disruptions. For example, if you have a tidal disruption event, the star that is making the tidal disruption event, the orbital period, I will try to explain why, is about 10 to the 5 years. So even if you make a star on a tidal disruption orbit, after 10 to the 5 years, it's destroyed. It arrived close to the supermassive black hole and got destroyed. So you need to supply a new star. So I'll talk about these processes that supply new stars into these weird orbits. And I will try to estimate the rates of each of those events. So what is the setup that I'm considering, the theoretical setup? A bath of stars with some velocity dispersion. And you put a supermassive black hole inside this bath of stars. So let's say in our galaxy, you take stars with velocity dispersion of 200 kilometers per second, and then you put a 4 million mass, solar mass black hole in the center of it, and you ask how will the stars distribute themselves around that supermassive black hole. There is the concept of radius of influence of the black hole. So let me go through this. It's a very simple one. Suppose that the bath of stars is infinite. It's very big, the size of the galaxy. And then you put the supermassive black hole at some point, at the center, let's say. If you go very close to the horizon of the supermassive black hole, there is just the supermassive black hole, nothing else. As you go farther and farther out, you see, oh, there are some stars around it. As you go farther and farther, there are more and more stars. Eventually, there is the radius where the total mass of stars is equal to the mass of the supermassive black hole. So this is where the potential of the supermassive black hole dominates. Farther than that, it's the potential of the stars that dominate because they are more massive than the supermassive black hole. So this is the radius of influence. So you can, if you know the density of stars, you know what is the radius of influence. In our galaxy, the radius of influence is about 2 parsecs. Just to give you scales in our galaxy looks like that. This is a few kiloparsecs. We're located 8 kiloparsecs away from the galactic center, as I showed from the first observation. So if we walk in parsecs, this is 8,000. This is maybe 2,000. And the supermassive black hole is here. The radius of influence is the size of this dot, because it's only 1 parsec. And it's within that dot that I'm trying to understand what is happening. Okay, it's the very, very center of the galaxy. It's not this. I'm talking about what is happening in this point in the middle. So that's the radius of influence. And for simplification, I will start with a system that all stars have the same mass. And then I will deal with systems where there are several masses. Questions? So there are very famous papers that try to answer this question. If you take a system exactly like the system I described, all stars have the same mass. There's one gravitating object, the supermassive black hole. How would the stars distribute themselves around it in a steady state situation? And these two papers by Peebles, by Bacall and Wolf, we're trying to study exactly this question. They got to 2 different answers. Peebles thought that the density profile of stars is going like R to the minus 9/4. And Bacall and Wolf, I think a year or 2 later, said, no, minus 7/4, not as steep as you think. So let me try to walk you through these 2 arguments and then convince you which one is right. So what Peebles said, he said the following: okay, these stars are going to scatter each other, but we're looking at a steady state situation. So the rate of scattering of stars per unit time that gets scattered from each radius should be the same in order to allow for a steady flux of stars onto the supermassive black hole. So what he had in mind is that there is a bath of stars outside the radius of influence. Inside the radius of influence, they all slowly diffuse by scattering between stars towards the supermassive black hole. So he wrote the following equation. If the stars at some distance r have velocity v, then gm, m is the mass of the stars out of the supermassive black hole, gm over v squared is the distance from one star that another star will pass and get deflected significantly. So this is the scattering distance, the distance for strong scattering. You square that, that is the cross section for strong scattering. So then you write n sigma v, or rho sigma v. This is the rate of scattering per star. And if you multiply that by the number of stars, or r cube, you get the rate of scattering at that distance, not per star. So this is the rate of scattering of stars at any distance from the supermassive black hole R. And in Peebles' mind, that is the flux, and it has to be constant. So you write this is now writing the same thing. This is constant. V as a function of R, we know, because within the radius of influence, the potential is given just by the supermassive black hole, and therefore V just scales as R to the -1/2. So we know V, and that allows us to get this, and saying this is constant leads to this. Okay. Bacall-Wolf, okay, now he said more or less what I wrote here. Bacall and Wolf did not say what I write here. I'm writing a very simplified version of what they're saying. They did an actual calculation of all the scattering processes from all different orbits that could be around the supermassive black hole, but it essentially comes to this. Exactly the same equation like before, but multiplying by the energy per object, E of R, which falls as 1 over R. So if you compare this to this, you have 1 over R less here. So instead of 9/2, 7/2, and therefore you get this one. So basically, Peebles is saying constant flux of stars, and the solution of Bacall-Wolf is a constant flux of energy of stars, not of the stars themselves. And it turns out that this is the more important criterion, because as you try to shove stars into the supermassive black hole, the energy per star becomes larger and larger. So it's the energy that is the biggest barrier than just the scattering. So let me say it in different words. If you look at the radius of influence, in the mind of Peebles, whenever you have a scattering at the radius of influence, you can transmit a star to closer into the supermassive black hole. But what this is saying, no, this is impossible. Because if you think of this star that has to go all the way to the supermassive black hole, at the end, the energy that it needs to lose is 1,000,000 times bigger than the energy it has here. So in order for the scattering at the radius of influence to transmit that energy outward, you need 1,000,000 scattering, not one scattering. So this is why this is now believed to be the correct power law. Okay. Well, this is not enough for us, because we don't just want to know how many stars we have at each distance from the supermassive black hole. We're interested in the existence of very eccentric orbits, because to have tidal disruption events, we need very eccentric orbits, not circular orbits. To have hypervelocity star formation, we need very eccentric orbits. And also, these processes just discuss two-body scattering around supermassive black hole. But when you get close enough to the supermassive black hole, the emission of gravitational waves itself changes the orbits of the objects around the supermassive black hole. And this is not taken into account here. So we want to include that. So to understand whether the emission of gravitational waves is important or where it is important, you can calculate the two-body scattering rate. This is equivalent to what I wrote before. You can calculate the time scale for a body to emit enough gravitational waves so its orbit will change. And if you equate those two, you write just this equal that, you get a very simple solution. And I'll show you this solution in the figure that will be the basis for the rest of the talk, the last 10 minutes. It's this figure. Okay, so what is this figure? These are all the possible orbits around the supermassive black hole within the radius of influence, both circular orbits and eccentric orbits. Each point on this figure is an orbit. Let me explain. So this is the semi-major axis, how big the orbit is. This axis is the periapse distance, the closest approach distance of that orbit. So for circular orbits, the semi-major axis and the closest approach distance are the same. The orbit is a circle. This is this line. The closest approach can never be bigger than the size of the orbit. So there are no orbits in here. It's mathematically impossible. If you're on this line or close to it, you have a circular orbit. This is a log-log plot. So if you go from here to here, you are a factor of 10 times at the closer approach than the size of the orbit. So this is eccentricity of 0.9. This eccentricity of 0, 0.9, 0.99, 0.999, and so on. Okay. What are the scales that are relevant for this figure? This figure is made for our own galactic center. So I already told you the radius of influence, the size of this dot here, is just 2 parsecs. So this is 2 parsecs. The closest distance we can have to the supermassive black hole is the event horizon of the supermassive black hole. So this is the Schwarzschild radius. And everything here is scaled to the Schwarzschild radius. The ratio, the Schwarzschild radius for 4 million solar mass black hole is about 0.1 AU. The ratio between this and this is about a factor of million. So we have huge space between the radius of influence, even though it is just this small dot in here. The size of the supermassive black hole is 1 million times smaller than that. This is the line that I derived in the previous slide, where the time scale for changing orbits by gravitational waves is equal to the time scale of changing orbits by two-body scattering. So let's see what it means. Below this diagonal line, you change the orbit by gravitational waves. Above this line, you change it by two-body scattering. Two-body scatterings of very eccentric orbits, they just tend to change the periapse distance, meaning you keep the semi-major axis fixed and you diffuse randomly according to which scattering you had in your periapse distance. So above this line, you just go up and down randomly by scattering of other objects. And gravitational waves are not very important. Below this line, gravitational waves dictate how an orbit evolves. And a very eccentric orbit under gravitational waves, it circularizes first. So the semi-major axis shrinks while the periapse distance remains fixed. So this is motion to the left in this diagram until the orbit circularizes and then it shrinks as a circular orbit. Okay, so the motion in this diagram is like this, up and down here, randomly, diffused way. If you get to hit this diagonal line, you turn left because of the action of gravitational waves, and the scattering becomes no longer important until the orbit circularizes. This is when you get close to this line, and then you shrink as a circular orbit until you hit the horizon of the supermassive black hole.
Did you try to simulate it numerically? I mean,
in what sense? Yes.
Yeah, all these
Short answer is
processes.
yes.
You did you show analytical calculation, but I couldn't run it on a computer.
Yes. So if you want to run an n-body system, if that's what you mean, with the parameters of our own galactic center, it's too difficult. But you can do a reduced system with fewer bodies, or you can do some simulations which are more statistical, which is what we did.
So what kind of what do you call statistical exactly?
Statistical is you say I'm following how many bodies I have. I have a parameter that tells me how many bodies I have in each semi-major axis. And then I'm following one star. I'm saying, okay, now it goes through this orbit. What is the chance that it will have a close approach with another body in here? And I say, okay, I do a Monte Carlo. I say, okay, it happened, but I don't do the real n-body simulation.
So you are not absolutely sure that your calculations are correct. It's only the order of magnitude.
I'm absolutely sure that they are correct. Why I was saying I'm not absolutely sure. The fact that they didn't do a simulation doesn't mean I'm not sure. I'm sure.
These are approximate calculations. They are not
Yes.
exact.
Yes. They are not exact. Yes. So, okay. The way I derived, for example, this line was very order of magnitude. I'm sure there are factors in here that are missing. But this calculation, for example, I've actually done more accurately.
So you have done the Monte Carlo simulations to get the same result?
No, still analytical, but more accurate in the sense that I wrote really the diffusion equation. Then I found a self-similar solution that combines diffusion and gravitational waves. And I treated the whole thing and I got something similar to this with some coefficient in here.
And why do you argue, your argument is that the solution is self-similar?
Self-similar in what sense? So I have here, so if you follow what is happening in here, there is supply of stars coming from different semi-major axes. If you provide this parallel in here, let's say from the Bacol-Wolf solution, I know what is the flux of them here. And all of them come in here and pair. So this and this and this behavior are the same. That's the self-similarity. So I'm saying this, the way that it turns in here, the way that it turns in here is the same. This is the self-similarity I applied. Therefore, I didn't have to solve a two-dimensional map, but only one-dimensional thing. And that allowed me to get some semi-analytic solution and to solve it more accurately. Yes.
What determines the width of these blue bands? For example, on the top part of the blue bands,
Yes.
there's a flaring up.
Yes.
What is the
So
reason?
let me try to explain. So here, the orbit is roughly circular. So when you scatter by a passing of another star, you change both the energy and the angular momentum. And the rate for both is similar. So you can move both in energy and in angular momentum in about the same way. This is here. When you already have, for some reason, a very eccentric orbit, so when you're very well below this line, there's a very strange orbit. Usually people would ignore them, but we're interested in these orbits. That's why I'm pointing. They're real. Most of the objects are in here. Very few are in here. But if you have an orbit like this, it means an orbit that has almost a radial orbit to an amazing precision, 0.9999 eccentricity. So any change in the velocity here, small change, would not change the energy a lot, but it would change the angular momentum a lot, and therefore only the angular momentum diffuses. So at each place in here, you can say how much would the energy change with a small scattering of the velocity and how much would the angular momentum change. And because this is already very eccentric orbit, the angular momentum will change more. So it will mostly go up and down. Now here, you try to feel the gravitational waves. So gravitational waves, they change the energy and not the angular momentum. And therefore, they take you to the left while the scattering is still going on. So that's why you get this width in here. So here it's because of the combination of energy and angular energy by gravitational waves and angular momentum by scattering. Here, the scattering themselves do both energy and angular momentum. Here, the scattering do only angular momentum. Here, the gravitational waves do only energy. Therefore, it's narrow again, and so on.
Scattering is isotopic.
Scattering is random. Yes. There are two stars just passing, so it could pass above, below, to the left, to the right. Okay. Now, if we go back to all these amazing phenomena that I described before, we can map them in here. Where are the tidal disruption events in this map? So we need to mark the tidal radius. This is this dashed line. Remember, we talked about the tidal radius in one of the first slides here. It's about 1 AU, about 10 or 20 times the Schwarzschild radius. Oh, it's also the calculation written on the board there. It's the size of the star or the size of the binary times 100. This is this. So anything that approaches to the supermassive black hole below the red dashed line will be destroyed as the tidal disruption events. So who can do that? You can have objects from here. Actually, most of the objects are in here. Most of the objects have circular orbits, and most of them have large semi-major axes. Despite this profile, because it's not as steep as r to the -3, when you multiply density by r cubed volume, you get most of the objects are outside. So most of the objects are here, but some of them do have eccentric orbits because of scattering, and they go up and down, up and down, up and down. Oops, they hit this, it's a tidal disruption event. Same here. They can do this, up and down, oops, a tidal disruption event. But here you cannot. You scatter up and down by random scattering of other particles. Oops, you hit that line. Now gravitational waves take over. You go to the left and you were saved from being a tidal disruption event. So from this point on, inward, there are no tidal disruption events. So all the tidal disruption events we see are for extremely eccentric orbits. They are these guys. They cannot happen here. They're only here. Where are these objects orbiting supermassive black holes that emit gravitational waves in the LISA band? They are here. How do they form? Probably from these guys coming down, doing this. Where are the QPs? QPs, at least in some of the models. So now QPs, I'm less sure because I don't know what QPs are. But let's take the model that a QPE is a star that just barely penetrates its tidal radius and spills mass every time. So it means it's just hovering above the tidal radius, or just below the tidal radius, so somewhere here. So the sources of this are these objects. And you can map everything. So you can make a connection between all these various phenomena. If you think of repeated TDs, there must be also somewhere in here. So if we talked about a continuation between QPs, monthly QPs, repeated TDs, and TDs, these are all objects sitting along this line. And you can see from this figure, where do they come from and how does it all operate. I want to go back to gravitational wave sources. So for that, I need to make the picture a little bit more complicated by putting both stellar mass black holes and stars around the supermassive black hole. And here we have a huge uncertainty immediately because we don't know how many stellar mass black holes are inside this inner dot here, in the inner parsec around the supermassive black hole. If you just take a usual initial mass function, then maybe 1 of 1,000 stars is a stellar mass black hole coming from a supernova of some massive star. But is it the same in the galactic center? I don't know. And people argue about that. So I won't go into this, but what we did in this calculation is we calculated the segregation between heavier objects, which are the stellar mass black holes. So we think of them as being 10 solar mass black holes, and the stars, of which we think as 1 solar mass black holes. 10 solar mass black holes, because they're heavier, due to this scattering, they tend to sink towards the supermassive black hole more than the stars. You can think of it this way because at a given distance from the supermassive black hole, the star, the light star, and the stellar mass black hole, the more heavy object, they will have the same velocity because the velocity is only given by the distance from the supermassive black hole. When they scatter, they tend to go to equipartition in energy. But if those two objects have the same velocity, it means that the heavy object has a lot more energy than the light object. When they scatter, it means that the heavy object, because it tries to go to equipartition on average, the heavy object will lose energy. Losing energy meaning going down in the potential well towards the supermassive black hole. So this is why this segregation happened. And you can do a sophisticated treatment of this, come up with this solution. Oh, I didn't show the other figure. I want to show this one. Then we'll go back to this one. So this is what we think is actually happening. And there is a interesting finding in here. So these top lines are the distribution of stars around the supermassive black hole in the presence also of stellar mass black holes, which are 10 times more heavy. And this thing below is the distribution, you can think of it as densities, of the stellar mass black holes, of the more heavy objects. So the more heavy objects are more rare. This is why they are below. And you see that they have a very weird behavior. So what happens here? Here, actually here, this is far from the supermassive black hole. This is close to the supermassive black hole. Here, on the outskirts of the radius of influence, there is this phenomenon of segregation that I described. The massive black holes, the stellar mass black holes, which are 10 times the mass of the stars, they sink. So that's why they are more and more concentrated toward the center. Let's follow just one of these curves, for example. Now let's do the red one. Because of this segregation, they become more and more concentrated towards the center. As you go far enough to the center, they become so concentrated that they now dominate the scattering. So outside of this point, it's the stars that do the scattering, and the black holes are just too rare. When you go further in, the black holes become so concentrated that they dominate the scattering. Yes?
So does this process screws up the power -7 divided by 4 found?
I'm getting there. So external to this point, here, this is the power 7/4, the Bacall-Wolf profile for the stars. And the black holes are negligible. There are too few of them. They don't do anything. But they sink towards the center. They sink until they become the dominant objects. When they do that, the black holes sit on the Bacall-Wolf profile. So now they have this profile. So now the 7/4 is for the black holes. And you can ask, what are the stars doing when the black holes have 7/4 and the black hole dominate? It turns out the stars are sitting on a 3/2 profile, slightly flatter, not a huge deal. And eventually, close enough to the supermassive black hole, the black holes start to fall in by gravitational waves. They fall below that purple line that we had in the two-dimensional diagram, and therefore there are fewer and fewer of them. The interesting thing is that in this region, the density of stellar mass black holes is independent of their total number. How does that come to be? So these are the difference between these three curves. Here I assume very few stellar mass black holes, 10 to the -4 compared to the stars. Here 10 to the -3 compared to the stars, and here 10 to the -2 compared to the stars. So many, average, very few black holes. But they always sink to the center until they dominate the scattering. When they dominate the scattering, they go to the Bacall-Wolf profile. So if there are many of them, they sink, and very soon they dominate the scattering and sit on this Bacall-Wolf profile. If there are very few of them, they will have to sink further in, and only then they become on the Bacall-Wolf profile. But once they do that, they all sit on the same curve. So basically what I'm saying is that I know the density of stellar mass black holes close to the supermassive black hole, even though I don't know their total number. A cute result. And this result allows me to calculate the sources for LISA with a higher certainty, because the spread between the different results that are how many black holes I have in total doesn't matter so much. At the center, it's more similar. And that allows us to come with this prediction. This is a Monte Carlo simulation of how many black holes I have emitting gravitational wave in the LISA band at each frequency. So this black line is the LISA sensitivity curve. Okay, everybody is familiar with this? What is this? What is this then? White dwarfs in our own galaxy that provide so much gravitational waves in this frequency, in millihertz frequency, that it confuses. It's a confusion source. It's like a noise for LISA. What we're finding in here, that actually the sources from galactic centers, not our own galactic center, but galactic centers in the universe, stellar mass black holes is comparable with that. And actually, you see that the number of sources in here is so dense that we actually say there is another source of noise for LISA at around the same frequency. So we think LISA will provide observations like that of stellar mass black holes around supermassive black holes in galactic centers. We predict detection of about 1,000 objects based on this theory. So I will end with that. This is like a summary of what I told you. I'm after time, so I will skip this. These are all the phenomena that I described. And while you're asking questions, I will just show you this nice movie again. Thank you.
Questions or comments?
So what is the time scale for which the evolution occurs? For example, in the 2D plot, the stellar eccentricity increases rapidly. The time scale should depend on the radius, but what is the typical time scale?
Yes, it's an important question because actually it's a little bit of a weak point. So here, the two-body relaxation timescale is about the age of the universe. Okay, so the basic assumption of steady state is just barely okay here. As you go farther and farther in, it becomes shorter. So here, steady state is more correct. Here, it's about the time scale for scattering is about 10 to the 10 years. So maybe it's in steady state, maybe not. If there are enough heavy objects that I haven't included in here, they accelerate the scattering, and then maybe it's less than 10 gigayears. But otherwise, it might be a little bit too long. So to go from here to here, it takes about 10 gigayears.
10 gigayears.
Yes. To an order of magnitude, this is the orbital time at this distance, which is 10 to the 5 years. This is written in here? No. So the orbital time at the parsec away from the supermassive black hole, this is here, is 10 to the 5 years. And the relaxation time is the orbital time times the number of objects at the radius of influence. The number of objects at the radius of influence by definition is 4 million, because each object is one solar mass and the supermassive black hole is 4 million solar masses. So because we have at the radius of influence by definition total mass of stars equal the mass of the supermassive black hole, we have 4 million objects. So 4 million times 10 to the 5 years is about 10 gigayears.
If you had to simulate it, you would need to simulate 4 million stars.
Yes, that's why it's difficult. For million
Can you
orbits.
use the mean orbit? You know, when you approximate the orbit of a star by an ellipse, the Gauss method, when you gain one dimension. Can you use that?
Yes, but this is two-body scattering, so you will lose the two-body scattering, and I want the two-body scattering.
But the two-body scattering is changing the ellipticity anyway, no? Of the orbits.
It's changing the ellipticity, the two-body scattering.
But does it change the major axis of the orbit?
In principle, yes, this is with this width, but if the orbit is already very eccentric, it doesn't change the semi-major axis so much.
Okay.
Yeah.
You comment on hypervelocity stars in this problem. Hypervelocity stars may come from binary.
Yes, hypervelocity stars. I don't think I have there is some slide somewhere on this, but basically, so it depends on the binary separation. Okay. So here is the tidal radius for a single star. If you have a contact binary, then this is roughly also the same tidal radius for the contact binary. So slightly above this. If the binary is well separated, it may be well above this. So it's a mess in this figure. That's why they're not here. But the easier thing to talk about is what happens to the star after the destruction of the binary. So there are two stars. When you separate the binary, one star flies out as a hypervelocity star, so it's not in this diagram, but the other star remains bound to the supermassive black hole. So you can ask, where would that star be? And that turns out to be another line in here, which is just a factor of 100 below this line. It's like this. What is the 100? 100 is m over m to the 1/3. M of the supermassive black hole over m of the star to the 1/3. So whether you populate it here, here, or here, or here, depend on how tight was the binary. So basically, most of the hypervelocity stars would come from binaries with this semi-major axis. They would go up and down in here until they are dissolved. If they are contact binary, they dissolve here. If they are somewhat larger than contact binary, they dissolve here. And then the ejected object is a hypervelocity star, not in this diagram. The surviving object keeps the same periapse distance and comes to this line. So it's a jump from here to here. This is the surviving object. So you go up and down here until you dissolve, depending where you dissolve, depending on your separation. And then you move to this line at the same horizontally.
The eccentricity of the disruption is especially determined by the mass ratio. I mean, the m divided by m.
Yes, so with m over m of a million, the eccentricity of the surviving object is 0.99, always. And this is why it's a factor of 100 below this line. So this is E equals 0, this is equal 0.9, this is equal 0.99. All the surviving objects are here. And this is an important discussion because people speculate what is the source of the massive objects that they see in the galactic center. Because at least in the beginning of the observations, they could only see 5 solar mass objects. And they don't live for too long. They don't live for 10 gigayears. So they cannot just scatter into there. They need to jump into there by some mechanism. One of the possible mechanisms is this Hill mechanism, separate a binary, and therefore bring directly to this close to the supermassive black hole these stars. So, but that would create very eccentric stars, more eccentric than what they see. And then the hope is that in the short time scale that they live, 10 to 100 million years, there will be enough scattering to reduce their eccentricity from 0.99 to 0.9 like SO2 has. So this discussion is very important.
I don't understand the last figure you showed. So the Lisa sensitivity. Many points, and each point is a black hole.
Okay, so the points is just a demonstration. The actual calculation is these lines. So above these lines, I expect to find one object per decade of frequency. So you see just maybe one here, one here, one here, one here, and one here. Each point is as a source that Lisa would find. But this is a statistical thing, it's not real.
It does not consider the binary, so just a
Single stellar mass black holes orbiting supermassive black holes very close to the horizon. Okay. The left-hand side of this figure,
no segregation. So what one
this is the result of segregation.
segregation? Okay.
So to calculate this, we go through this figure.
Okay.
And the sources that I'm plotting there are mostly here, close to the supermassive black hole. And left side of this figure, they are low frequency. Low frequency usually means far from the supermassive black hole. Far from the supermassive black hole, emission of gravitational waves is weak. Time scale for evolution is long. They will not evolve over the Lisa time. So they will be steady sources in Lisa. Here, Lisa would actually see them as evolving sources. You would start detecting them here and they would evolve as time goes on. So you'd see a streak. So they won't have just a single frequency. They will start at this frequency, but evolve. This is why there is a break in the prediction of how many in this and this, non-evolving and evolving.
So if df equal 1000 means
Above this line, there are 1000 sources.
1000 sources. So okay. So observe one year. Then below 10 to minus 3. No.
So the 1 year is not so important in here, only in the sensitivity of Lisa. So this sensitivity is if you accumulate the observation of Lisa over 5 years,
Yes.
which is the some duration of Lisa mission.
So, but in order to have a confused background noise, so every so in
The confusion is not plotted in here, but there will be confusion here. So here it means, okay, so each point in here will have some uncertainty in frequency.
Yeah.
Because the duration of measurement of Lisa is finite.
Yeah.
So 1 over the 5 years is the measurement error in the measure of the frequency of a source. If you have 2 sources within that uncertainty, then you're confused.
Yes.
You cannot distinguish it. 2 sources will look like 1.
Confusion is only
That corner is
Okay.
so dense, it will confuse and it will increase the sensitivity.
Okay.
This sensitivity curve is taken from some Lisa
I see.
site. So this only includes the instrumental things and the white dwarfs,
Okay.
which
So
people know.
above that, so they are all resolved. And
These are resolved, yes. So in principle, I could, for each point in here, put some width, the error bar, and you would see that this is resolved from that.
we expect many M resources.
Yes. 1,000.
Okay. Okay.
1,000. So, so something like in here is not a detection because it's signal to noise is 1. So things that are closed here, they are not detections. So you need to go maybe a factor of 8 above. So, but these are detections because it's more than a factor of 8. And there are thousands in here.
Many sources. I see.
Which is great for this rate.
It's surprising.
Too bad that it's 2037. I wanted more.
Why do you stop z equal 1?
Just because it's I didn't finish this work. So this calculation assumes Euclidean universe. So if I want to know how many sources I have, I assume constant uniform density of sources, and that is only correct until z equal 1. So that's why you see more and more sources. As you become weaker and weaker, you can see farther away, more sources. But above z equal 1, this Euclidean geometry is no longer correct. I have to modify it, and I didn't do it yet. So I don't put cosmology in this figure, not density of galaxies, not evolution of galaxies, nothing, no cosmology here. So this just assume constant density of galaxies from here outwards. So that's only correct to z equal 1. So that's why I put where the sources are z equal 1.
I see. Any other questions or comments? Not. Thank
you very much.
Fantastic.